High in the Andes, stone walls built without any mortar have survived massive earthquakes for centuries. This is the enduring mystery of Inca architecture. We are standing amidst one of the most seismically active landscapes on the planet, where the ground itself is a constant, unpredictable threat. Yet here, ancient structures not only remain but defy the very forces that routinely level modern cities. This video is an investigation into the forgotten engineering principles behind that astonishing resilience. By the end, you will understand the precise, brilliant techniques that made these walls virtually earthquake-proof and what our own engineers are rediscovering today. How did a civilization without iron or the wheel achieve such perfection in stone? And what does their silent, steadfast work teach us about building for an unstable world? What does true resilience look like when it's carved from the bones of the earth itself? The ground beneath the Inca Empire was never still. It was a living, shifting entity. The Andes Mountains, a colossal spine of rock thrust upward by the slow, grinding collision of tectonic plates, are not a quiet monument to the past. They are an active, unfinished work, and this geological reality meant that powerful tremors were not rare disasters, but a regular fact of life. For the Inca, building a civilization here was an act of profound defiance. They weren't just constructing temples and storehouses, they were anchoring an empire to a landscape in perpetual motion. A single catastrophic quake could shatter supply lines, collapse vital administrative centers, and unravel the very fabric of their centralized control. So, earthquake resistance transcended engineering. It was a direct imperative for survival and for imperial stability. The architecture they developed, therefore, wasn't merely impressive, it was absolutely essential. Every stone they fitted was a response to a question the earth asked with violent regularity. How do you build a forever on ground that constantly threatens to forget you? This constant environmental challenge is what makes their silent, steadfast achievements not just beautiful artifacts, but a masterclass in listening to the land and learning its rhythms. To witness the answer, you need only walk the perimeter of Sacsayhuaman. This fortress complex, towering above the old Inca capital, is not just a structure. It is a declaration carved directly into the mountainside. Its most famous feature is a series of 3 colossal, zigzagging walls that run for hundreds of meters. They look less like something built and more like something that simply grew from the bedrock, a natural extension of the earth itself, and that is precisely the point. These walls are the ultimate case study, the perfect laboratory for understanding Inca seismic genius. What you see here in the staggering scale and impossible precision is not random artistry. It is a visible, tangible demonstration of every core principle we are about to explore. Each stone in these walls is a character in the story, and their arrangement is the plot. They are enormous, some weighing over 100 tons, and their shapes are wildly irregular, like pieces from 1,000 different puzzles. Yet they fit together with a seam so tight, so flawless, that even after centuries you cannot slip the edge of a piece of paper between them. This is the mortarless marvel. It is a feat that seems to defy logic, and for a long time modern observers assumed it must have required some lost, almost magical technology. But the truth is both more sophisticated and more grounded. Sacsayhuaman is a textbook written in stone, and we are finally learning how to read it. The secret to that impossible fit lies in a deliberate choice of chaos. While many ancient cultures, from the Romans to the Egyptians, perfected the art of the rectangular block, stacking uniform bricks or ashlars in neat, horizontal rows, the Inca architects did something radically different. They embraced irregularity. Their technique is known as polygonal masonry. Look closely at any of these great walls, and you will see that the stones are not simple cubes or rectangles. They are multifaceted, each one a unique polygon with anywhere from 5 to 12 or more sides and angles. The faces are slightly convex, and the edges are beveled. This creates a three-dimensional jigsaw puzzle of staggering complexity. Now, imagine the difference between two walls during an earthquake. A wall built with uniform rectangular blocks is rigid. Its joints are straight, vertical lines of potential weakness. When seismic waves pass through, that wall wants to sway as a single, monolithic unit. But the mortar holding it together is brittle. The force finds those straight seams, the weak points, and the entire structure can crack and topple in a single, catastrophic failure. The Inca wall, however, is an entirely different entity. There are no long, straight, continuous joints. Instead, each stone locks into its neighbors with a network of tiny, angled interfaces. The force of a tremor cannot travel in a straight line. It is forced to dissipate along a labyrinth of interlocking angles. Each irregular polygon micro adjusts, rocking and settling slightly against its uniquely shaped neighbors. The energy is diffused, transformed from a shattering blow into a series of tiny, accommodated movements. The wall does not fight the earthquake. It dances with it, a slow, grinding waltz that ends with the stones settling back into place, still holding each other tight. This is the genius of the polygonal puzzle, a system where perceived chaos creates ultimate stability. But achieving that perfect, interlocking fit required more than just selecting the right stones. It demanded a sculptor's patience and a physicist's understanding of force. The Inca were working with andesite and granite, some of the hardest stones on the planet, harder than the iron they famously did not use. So how do you shape a material that resists your strongest tools? The answer lies in a methodical, almost meditative process of persuasion, not domination. They began with hammerstones, themselves made of even harder rock like quartzite. A worker would strike a precise point on the face of a new block, not to smash it, but to carefully spall off small flakes. With thousands upon thousands of controlled, glancing blows, they could gradually reduce a stone to a rough shape. But the final precision, that breathtaking seamlessness, came from abrasion. They likely used sand, water, and possibly crushed quartz as a grinding paste, painstakingly rubbing stone against stone for untold hours. The goal was never a perfectly flat, polished exterior face you could see. That was irrelevant. The entire focus was on the hidden, inward-facing contact points where one stone would meet its neighbor. They were creating a three-dimensional negative space in one block to receive the unique positive form of another. Think of it not as carving individual statues, but as carving a single, dispersed lock and key system across an entire wall. Some researchers also suggest they may have used thermal fracturing, applying intense heat with fire, and then rapidly cooling the surface with water to cause controlled cracking along desired planes. This combination of percussion, abrasion, and possibly thermal shock allowed them to achieve a fit so precise that the contact between blocks often exceeds 80%. That is an almost inconceivable level of craftsmanship. The stone was not just cut, it was convinced slowly and relentlessly to become part of a greater, unshakable whole. This difference in design philosophy creates two entirely distinct reactions to the same seismic threat. Think of a wall built with uniform, rectangular ashlar blocks. It is a grid. The stones are stacked in neat, horizontal courses, one directly on top of another, held together by mortar. This creates a structure that is strong under simple, vertical compression, like the steady weight of a roof. But an earthquake does not apply a steady force. It sends complex, shearing waves through the ground, a violent back and forth or up and down motion. In that grid-like wall, the mortar between the blocks forms straight, continuous lines of weakness, like perforations on a piece of paper. When the shaking begins, the entire wall wants to move as one rigid unit. The brittle mortar cannot flex, so those straight lines become the exact paths where cracks initiate and propagate. A single fault line can race up a vertical joint, and once it starts, it has a clear, unobstructed path to follow. The failure is often total and catastrophic as the neat grid becomes a pile of rubble. Now look again at the polygonal wall. There is no grid. There are no long, straight lines. Instead, each irregular stone is locked in place by its uniquely shaped neighbors on all sides, above and below. The forces from an earthquake cannot travel in a straight line. They are confronted with a labyrinth. When a tremor hits, the energy is immediately channeled in multiple, crisscrossing directions. A force moving upward is deflected sideways by an angled interface. A lateral shove is redirected downward into the foundation. The stones themselves can undergo tiny, individual rotations and micro-adjustments, absorbing the energy through friction and minute movement at thousands of contact points. This prevents any single crack from gaining momentum. It is the architectural equivalent of a net versus a pole. A single, solid pole will snap under a strong lateral force. But that same force applied to a net is dissipated across countless interconnected fibers. No single thread bears the full brunt. The polygonal wall is that net woven from stone. The genius is not in preventing movement altogether, which is impossible, but in designing a system that welcomes and neutralizes that movement through a chaotic, interlocking dance. The wall settles, it grinds, it shifts by millimeters, and then it finds stillness again, its pieces still perfectly in embrace. Where the ashlar wall presents a single, brittle face to the earthquake, the Inca wall offers 1,000 stubborn, interlocked shoulders. This three-dimensional network is where the engineering becomes truly elegant. Each uniquely shaped stone does more than just touch the ones beside it. It is designed to engage with its neighbors on multiple planes, often with dovetail-like protrusions and corresponding recesses that are invisible from the outside. Think of it not as a wall, but as a single, massive sculpture that has been carefully sliced into pieces and then perfectly reassembled. The joints are not merely seams, they are intricate, load-bearing interfaces that lock the entire assembly together in all directions. This creates a phenomenon engineers call modular interlock. The individual blocks or modules are so thoroughly interconnected that they cease to behave as separate entities under stress. When seismic energy enters the base of such a wall, it does not travel up through isolated vertical columns. Instead, the energy is distributed laterally across this dense, three-dimensional mesh. The entire structure begins to move as a single, coherent mass. This is a critical distinction. A loosely stacked pile will shake apart because its components can move independently, crashing into each other until they fall. But a perfectly interlocked mass moves in unison, like a person shifting their weight to maintain balance on a rocking boat. The inertia of the whole system resists being thrown into chaotic, disaggregating motion. The wall sways, it may even tilt slightly, but its internal bonds hold firm because every stone is sharing the load with every other stone around it. The architecture has achieved a kind of unity, transforming a collection of individual rocks into a new geological entity, one that has learned how to stand together against the chaos of the earth. Yet even the most perfectly interlocked wall would be vulnerable if its foundation failed. The Inca understood this with a clarity born of necessity, and their solutions reveal a profound grasp of how forces travel through the earth. They knew that a tremor's destructive power begins deep below the surface as energy pulses upward through the ground. To stop it, you must meet it at its source. So, before a single stone was shaped for a wall, the Inca builders performed a kind of architectural acupuncture on the landscape itself. They often chose to construct directly upon the living bedrock, carving foundations and terraces straight into the mountain's bones. This wasn't just for a level surface, it was to create a direct, unbroken connection between their structure and the most stable layer of the earth. Think of it as tying a boat directly to the ocean floor instead of to a floating dock. The building becomes an extension of the immovable mass below. But they went even further. In places where the bedrock was too deep or the soil unstable, they engineered dynamic basements. Archaeologists have found sites where the foundation consists of carefully layered gravels, with stone sizes graduating from large boulders at the bottom to smaller stones and compacted earth above. This created a flexible, draining base that acted like a shock absorber. When seismic waves rippled upward through this engineered substrate, the energy was scattered and dampened by the countless interfaces between the different-sized stones. Much of the shaking's intensity was simply consumed by the friction and minor shifting within the foundation itself, never reaching the precision-built walls above. It was a brilliant form of sacrificial defense, a buffer zone that took the initial brunt so the masterpiece could remain unscathed. But the genius of this system extends far beyond the walls themselves, into the very spaces they create. Walk through any Inca structure, from a humble storehouse to the grand halls of Machu Picchu, and you will notice a consistent, defining feature. Every single opening, every doorway, every window niche is shaped not as a rectangle but as a trapezoid. The sides slope inward as they rise, and the base is wider than the top. This is not an artistic whim or a simple architectural style. It is a calculated and brilliant response to the physics of an earthquake. In a rectangular doorway, the weight from the wall above is transferred straight down through the vertical sides onto the lintel, the horizontal stone beam across the top. During violent shaking, that lintel is a vulnerable point. It can bounce, rotate, or simply pop out of its seats as the walls sway apart, leading to a catastrophic collapse of the entire opening. The trapezoid solves this with elegant geometry. By slanting the walls inward, the structure inherently becomes more stable, its center of gravity lowered and pulled toward the interior. More importantly, the trapezoidal shape acts like a natural locking mechanism for the lintel stone. When seismic forces cause the walls to vibrate, the inward slope means any movement actually drives the lintel deeper into its tapered socket, wedging it more securely in place. The earthquake itself becomes the force that tightens the lock. It is a perfect example of designing with the chaos in mind, creating a form where the expected failure mode is literally designed out of existence. This principle was applied universally, from the smallest storage niche to the grandest ceremonial gate, proving that seismic resilience was a foundational rule, not an afterthought. Look closer still, and you might notice something curious on the faces of certain stones. Amidst the seamless joins, a few blocks feature a distinct, rounded protrusion left uncarved, a kind of stone knob. These are known as bosses. They stand out against the otherwise flush surfaces, and for a long time they were a minor puzzle. The most straightforward explanation is a practical one for the builders themselves. Shaping these multi-ton stones was a monumental task, and moving them into their final, perfect position would have been the ultimate challenge. The bosses likely served as handles. Ropes could be lashed around them, or wooden levers could be wedged beneath them, giving workers precious purchase to inch a block forward, lift it slightly, or make those final, microscopic adjustments needed for the perfect fit. Once the stone was set, the boss would often be pecked away, leaving a smooth face, but in many places they were left in place. This suggests their purpose may have been more than just construction aid. A boss left intact becomes part of the wall's final form, and here the theory becomes fascinating. That protruding knob is not floating in air, it is often seated within a shallow, corresponding indentation on the stone above or beside it. This creates a simple but effective socket system. During an earthquake, as the wall undergoes its complex, grinding dance, these bosses and sockets act as additional pivot points and restraints. They allow for a tiny, controlled amount of rotational movement, a few millimeters of play, before the geometry of the interlocking faces reasserts itself and pulls the stone back into alignment. Think of it like a wooden drawer that has a slight wobble. It is not a flaw, but the result of intentional tolerances that prevent it from jamming in its frame during changes in humidity. The bosses and sockets introduce a calculated, microscopic flexibility into a system that is otherwise defined by rigid, intimate contact. They are shock absorbers at the stone-to-stone level, a final, elegant refinement that ensures the great polygonal puzzle can flex without fracturing. This subtle feature blurs the line between construction technique and finished engineering, a reminder that for the Inca, the process of building and the principle of enduring were one and the same. This entire system of interlocking stones relies on a silent, constant partner, gravity. The Inca did not build static monuments meant to remain forever unchanged from the moment of their completion. They built dynamic systems designed to improve with age. The key to this lies in the initial, intentional imperfection of the fit. While the contact between stones was astonishingly precise, it was never 100% perfect at the moment of placement. There were microscopic high points, tiny areas where the stone surfaces did not yet meet fully. This was not a mistake, it was a crucial part of the design. Once the multi-ton block was set into its polygonal cradle, the immense, unrelenting force of gravity went to work. Over months and years, the sheer weight of the stones above, combined with the subtle vibrations of the earth itself, caused a gradual process of settling and compaction. Those microscopic high points would slowly grind against each other, wearing away in a process called wear-in. Think of a new leather shoe that is stiff at first, but after being worn for some time, molds perfectly to the shape of your foot, becoming more comfortable and secure with every step. The Inca walls performed this same process but on a geological scale. As the stones settled, the contact area between them actually increased. The joints became tighter, the friction between the stone faces grew stronger. What began as an expertly crafted puzzle became, over time, a single, fused mass. The structure literally grew stronger under its own weight, compacting into an even more unified and stable form. This self-tightening mechanism meant that the wall's resistance to seismic forces was not a fixed value on the day it was built. It was a quality that actively increased as the years passed. The earthquake resistance was literally built in by the earth itself, a slow, patient collaboration between human intention and natural law. The sheer scale of this ambition is almost incomprehensible. To build these earthquake-defying structures, the Inca first had to solve a problem of staggering logistics. They were not simply fitting stones found at a building site. They were extracting colossal blocks from mountainside quarries, sometimes located dozens of kilometers away across some of the most rugged terrain on the continent, and then moving them with a precision that modern engineers still marvel at. This was not the work of a few local artisans. It was a state-sponsored, empire-wide undertaking that speaks to a profound, deliberate engineering philosophy. Consider the quarry at Cachicota, across the river from the citadel of Ollantaytambo. Here, massive slabs of rose rhyolite were carved directly from the cliff face. Workers used stone and bronze tools to patiently channel around a block, then likely drove wooden wedges into the cracks and soaked them with water. As the wood expanded, it would create enough pressure to split the multi-ton block free from the living mountain. This was just the beginning. Now you have a stone weighing as much as 50 tons, resting on a steep slope hundreds of meters above a raging river. How do you move it? The Inca had no wheels, no pulleys, no draft animals larger than the llama, which cannot carry such loads. Their solution was a masterpiece of coordinated human effort and simple physics. They built extensive ramps and causeways, paving roads with fitted stones to create smooth surfaces. To move a single block, teams of hundreds of workers would likely have used levering poles, ropes woven from tough grasses, and a system of rolling logs. The stone would be painstakingly rocked onto a bed of lubricated wooden rollers, then pulled forward as workers behind constantly repositioned the freed logs to the front. It was a slow, rhythmic, monumental effort, an inch-by-inch conquest of gravity and distance, but the most critical step happened before the journey even began. At the quarry, stonemasons would perform a rough shaping of the block, creating its basic polygonal form and, most importantly, carving its complex contact faces. This was the trial fit. They were not moving anonymous rocks. They were moving unique pieces of a three-dimensional puzzle, each one predestined for a specific location in a wall they could not yet see. The logistics were not just about transportation. They were about the orchestrated flow of pre-engineered components across a landscape, a supply chain of stone where every piece was irreplaceable. This level of organization reveals a civilization that did not see construction as a series of separate tasks, quarrying, moving, building, but as a single, integrated process. The resilience was designed in from the very first strike of the hammerstone at the quarry face, a testament to an intention so vast it could only be fulfilled by the collective will of an empire. This architectural philosophy stands in stark contrast to the fate of many other ancient civilizations who built in earthquake zones. Across the world, from the Mediterranean to Asia, societies with advanced engineering knowledge constructed magnificent stone cities, often relying on strong mortar as their primary binding agent. When the earth shook, however, that very strength could become a fatal weakness. Consider the great classical temples of the ancient Greeks, masterpieces of geometry and proportion. They were built with precisely cut marble blocks, fitted together and sealed with iron clamps set in molten lead, a system designed for permanence. Yet during major seismic events, the rigid nature of these structures often led to catastrophic failure. The mortar and metal, while incredibly strong, created a brittle unity. When subjected to the complex, shearing forces of an earthquake, the entire colonnade might sway as one inflexible unit until the stone itself fractured or the rigid joints gave way, toppling columns in a domino effect of ruin. The historical record is filled with accounts of such magnificent places being reduced to fields of broken drums, their elegant geometry shattered by the very ground they stood upon. Similarly, in many parts of Asia, massive brick and mortar pagodas and fortifications, though engineered for vertical load, often proved vulnerable to the lateral chaos of a tremor. The mortar, once cracked, offered no way for the structure to settle back into place, leading to progressive collapse. The Inca solution was fundamentally different. They did not seek to create a rigid, unyielding monument to defy the earth. Instead, they designed a responsive, living system that could absorb, dissipate, and accommodate the Earth's movement. Where others built walls that stood against the tremor, the Inca built walls that could move with it. This distinction is not merely a technical footnote, it is the core of their enduring legacy. Their architecture accepted the fundamental truth of their environment, that the ground was not a passive foundation but an active participant. By designing for flexibility within an interlocking system, they achieved a resilience that rigid, mortar-bound structures, for all their grandeur, could seldom match. This comparative view reveals the Inca not as master stonecutters alone, but as profound students of force and motion, whose greatest innovation was humility in the face of nature's power. The true test of any engineering principle is not in the blueprint, but in the violent reality it must survive. For the Inca walls, that test arrived not once but repeatedly, in moments of profound and terrifying force. The historical record provides stark, comparative evidence of their success, written in the ruins of two different worlds. In the year 1650, a massive earthquake struck the heart of the former Inca Empire, centered near the city of Cusco. The shaking was catastrophic. For the Spanish colonists who had built atop the Inca foundations, it was a disaster. Their churches, mansions, and administrative buildings, constructed with rectangular bricks and thick mortar in the European tradition, crumbled. Towers collapsed, facades sheared away, and entire city blocks were reduced to rubble. The loss of life and property was immense, yet, emerging from the dust and devastation, something remarkable became clear. The ancient Inca stonework upon which much of the colonial city was unknowingly built had largely endured. The polygonal walls of the Coricancha, the Sun Temple that now formed the base of the Santo Domingo Church, held firm. The zigzagging bastions of Sacsayhuaman on the hill above showed only minor settling. The Spanish, in their rebuilding, often had no choice but to incorporate these stubborn, surviving Inca walls into their new structures, a silent and resilient skeleton refusing to be erased. 300 years later, history delivered the same lesson with modern witnesses. In May of 1950, another tremendous quake, one of the most powerful of the 20th century in the region, rocked Cusco once again. The pattern repeated with chilling clarity. Modern concrete and brick buildings, some of recent construction, sustained severe damage or complete collapse. Yet again, the pre-Columbian stonework demonstrated astonishing resilience. Photographs from the aftermath show piles of colonial-era debris littering streets, while in the background, the seamless, interlocked stones of Inca foundations stand unbroken, having absorbed the energy and simply settled back into place. These were not laboratory simulations. These were real-world, full-scale destructive events, and they served as the ultimate validation of the Inca engineering philosophy. The colonial architecture, for all its imported sophistication, presented a rigid, brittle face to the earthquake and was broken. The Inca architecture, designed for flexibility and interlocking movement, danced with the tremor and remained. The proof was in the standing stones, a quiet testament written across centuries, waiting for us to understand the language. So what does modern engineering, with all its computational power, make of these ancient stone puzzles? In recent decades, researchers have moved beyond simple observation to put Inca principles to the test in the lab. Using advanced computer modeling, specifically a technique called finite element analysis, they have digitally reconstructed these polygonal walls down to the microscopic imperfections in the stone joints. The software allows them to simulate the precise forces of an earthquake, applying complex waves of energy to the virtual structure and watching how every single block reacts. The findings are not just confirmations, they are revelations. The models show that the seismic energy entering the base of the wall is immediately and dramatically scattered. It does not travel upward in a clean, destructive wave. Instead, it fractures into countless micro-vibrations that travel along the labyrinth of interlocking joints, losing intensity with every deflection and redirection. The chaotic network of interfaces acts as a built-in damping system, converting the destructive kinetic energy of the quake into harmless heat through friction at the stone-to-stone contacts. Even more fascinating is what the models reveal about the structure's natural frequency, the rate at which it naturally wants to vibrate when disturbed. Inca walls, due to their massive weight and unique interlocking design, have a very low, slow natural period of vibration. Most damaging earthquakes, however, produce higher frequency shaking. This mismatch is crucial. It means the seismic waves are essentially out of sync with the wall's preferred rhythm, so the structure does not resonate or amplify the shaking. The energy cannot get a coherent grip on it. To bring this from the digital world into the physical, engineers have even constructed scaled-down replicas of Inca polygonal walls and placed them on massive shake tables, devices that can replicate the exact motions of historic tremors. In these dramatic tests, the replicas behave exactly as the computer models predict. They shudder, they grind. The individual stones undergo visible micro-rotations of a few millimeters, but when the shaking stops, the wall remains standing, its pieces settled back into a stable configuration. The rigid, mortar-bound control models built beside them often fail catastrophically. These scientific validations transform the Inca achievement from a historical curiosity into a timeless lesson in physics. The builders may not have had the equations, but they understood the phenomena with an intuition carved directly from experience, creating a form of passive seismic design that our most advanced software now applauds. But for all their brilliance, the Inca methods were not a magical shield against every earthly force. They existed within a specific, understood context, and their vulnerabilities reveal as much about their genius as their successes. Consider a tall, slender wall, built with the same perfect polygonal masonry but standing alone, without the lateral support of a larger structure or terraced buttressing. During an intense tremor, such a wall could experience what engineers call out-of-plane rocking. Instead of the stones grinding together in their interlocked dance, the entire wall could begin to pivot back and forth at its base, like a door swinging on its hinges. Once this rocking motion exceeds a certain threshold, the wall's center of gravity shifts too far and it can topple over in one piece. The Inca understood this limitation intuitively. That is why you almost never find freestanding, thin polygonal walls in their architecture. Their most resilient constructions are always part of a larger, interconnected system, low terraces, wide platforms, or structures built into hillsides where the earth itself provides lateral support. The masonry was designed for compression and interlocking shear, not for standing alone as a tall, slender monolith. Their engineering was holistic, considering the entire site as a unified system of stability. A single, perfectly cut stone was never the goal. The goal was an unshakable landscape. There was another, far more catastrophic threat that even the most ingenious masonry could not withstand, a failure not of the structure, but of the very ground it stood upon. In certain soil conditions, particularly loose, water-saturated sands and silts, the violent shaking of an earthquake can cause a phenomenon known as liquefaction. The vibration causes the water pressure between the soil particles to increase dramatically until the solid ground momentarily behaves like a liquid, losing all its strength and bearing capacity. Imagine a building standing on what suddenly becomes quicksand. No foundation, no matter how brilliantly engineered, can survive that. The entire structure can tilt, sink unevenly, or be swallowed as the earth turns to slurry beneath it. Archaeological evidence suggests that some Inca sites may have been damaged or abandoned due to such ground failures. This underscores a critical point. Their seismic resilience was a dialogue with a specific type of terrain, the stable bedrock and compacted gravels of the mountainsides. They mastered the art of building with the solid earth, but when the earth itself ceased to be solid, even their most resilient walls had no answer. This inherent limitation adds a crucial layer of nuance, showing that their technology was not a universal solution, but a profoundly sophisticated adaptation to the challenges they knew best. It was a partnership with the land, and like any partnership, it had its conditions. This balanced view does not diminish their achievement, it deepens our respect for it. The Inca builders were not infallible demigods. They were brilliant pragmatists working within the harsh realities of their world. They identified the most common and destructive seismic threat, the shearing waves that topple rigid structures, and they developed an elegant, passive system to neutralize it. They focused their immense effort where it would yield the greatest return, creating urban centers and ceremonial complexes that could weather the storms they knew were coming. The occasional failure due to liquefaction or an unsupported wall only highlights how intentional and context-specific their successes were. They did not seek to conquer every possible force of nature, an impossible task. Instead, they listened to the land, learned its most frequent language of violence, and crafted a response in stone that spoke directly to it. Their legacy is not one of perfect, unbreakable monuments, but of resilient, adaptable wisdom, a lesson in focusing our ingenuity on the problems we can actually solve and building a dialogue with the world as it truly is. This mastery of stone, however, was not a technology that could be packed away and saved for later. When the Spanish conquest reached its violent peak in the 1530s, it did more than topple a political empire. It shattered the very ecosystem that had produced this architectural genius. The Inca system was a seamless integration of knowledge, labor, and culture, and when that system was dismantled, the knowledge it held evaporated like water on hot rock. The first and most critical loss was the specialized labor system, the mita. This was not a simple workforce. It was a state-managed rotation where communities contributed labor as a form of tax. Through this system, master stonemasons, or kamayak, trained apprentices across generations in a continuous, living chain of expertise. A young worker might spend years moving stones before ever touching a hammerstone, learning the feel and weight of the material through his body. The knowledge was not written in books, it was encoded in muscle memory, in the shared rhythm of a team moving a 50-ton block, in the intuitive understanding of how a specific stone would ring when struck correctly. The conquest dismantled this organized, tribute-based economy. The Spanish introduced new demands like mining for silver, which consumed labor, and diseases that devastated the population. The continuous, generational apprenticeship that produced a master kamayak was abruptly broken. The living libraries of tactile knowledge, the men who could read a stone's grain and know precisely where to strike, were scattered, their roles erased by a new colonial order that had no use for their particular, time-consuming craft. Furthermore, the new rulers brought with them a completely different architectural vision and toolkit. The Spanish priority was not seismic resilience, it was speed, symbolism, and the display of a familiar European power. They sought to build churches, palaces, and grid-patterned towns that looked like home, using technologies they understood: brick, mortar, and timber. Their architectural language was one of straight lines, right angles, and ornate facades, a direct rejection of the polygonal, earth-hugging aesthetic of the Inca. Mortar, which the Inca had deliberately avoided, was now the essential ingredient. It allowed for faster construction with less skilled labor, as bricks could be standardized and stacked quickly. The intricate, year-long process of fitting two stones together became an absurd luxury in the eyes of colonists racing to establish their dominion. Why spend a month persuading a single boulder into place when you could build an entire wall of brick and plaster in the same time? The new technology was a declaration, a literal overwriting of the old landscape with a new cultural script. The sophisticated, passive seismic design of the Inca was simply not a value they recognized or needed to replicate, at least not until the earthquakes came and taught them a harsh lesson. Finally, the nature of the knowledge itself ensured its fragility. Inca engineering was an oral and practical tradition, a craft passed from hand to hand and eye to eye. There were no engineering manuals, no diagrams of stress distribution, no formal codification of the principles of polygonal interlock. The knowledge existed only in the doing. When the doing stopped, when the master craftsmen were no longer teaching, and the great state projects were no longer commissioned, that embodied wisdom had nowhere to go. It could not be archived in a library. It could only fade from memory with the passing of each generation that no longer practiced it. The Spanish, for their part, documented many things about the Inca world, but they were chroniclers, not engineers. They marveled at the fit of the stones in journals, calling it a work of demons or a lost art, but they did not, perhaps could not, systematically record the methods. The technique faded not because it was ineffective, The earthquakes would soon prove otherwise, but because it was inextricably linked to a way of life, a social structure, and a philosophical relationship with the earth that the Conquest sought to eradicate. The stones remained silent and resilient, but the conversation between the craftsman and the rock, the slow, patient language of their construction, fell into a silence that would last for centuries. The silent testimony of those standing stones eventually found its way to the desks of modern seismic engineers, and the conversation they started is reshaping how we think about building for an unstable planet. Today's engineers, armed with advanced materials science and computer modeling, face the same fundamental challenge the Inca did: how to keep a structure upright when the ground beneath it is in violent motion. While our solutions look different on the surface, the underlying physics they employ share a profound kinship with those ancient principles. We now design for energy dissipation and ductility, the ability of a building to deform without breaking. In a modern skyscraper in a seismic zone, this might mean incorporating steel frames with specially designed joints that are meant to bend and yield in a controlled way during an earthquake, absorbing the destructive energy as heat, much like the friction between Inca stones converted shaking into harmless grinding. We use massive dampers like giant hydraulic pistons placed throughout a building to counteract sway. These are high-tech answers, but the goal is identical: to prevent rigid resistance and instead allow for managed, non-catastrophic movement. The most direct echo of Inca wisdom, however, is in the concept of base isolation. This is where a building is literally decoupled from the shaking ground. It rests on flexible bearings, often made of layered rubber and steel, that act as a sophisticated shock absorber. When an earthquake strikes, the ground moves violently, but the building atop these isolators sways gently and slowly, its integrity preserved. This is the modern, materialized version of the Incas' graduated gravel foundations, a deliberate, engineered buffer zone that takes the first brutal impact so the structure above can remain serene. The philosophy is a mirror: do not fight the earthquake's energy, redirect it, absorb it, or let it pass you by. Some architects and engineers are taking this inspiration even further, looking past mere philosophy to directly resurrect the form. In a fascinating convergence of ancient wisdom and cutting-edge technology, researchers are actively exploring contemporary buildings that use interlocking, mortarless components. The motivation is powerful. Such structures could be more resilient, more sustainable by avoiding carbon-intensive cement, and even reusable, as blocks could be disassembled and reconfigured. Projects are experimenting with precisely machined stone or concrete blocks that fit together like three-dimensional puzzles, often using geometries inspired by Inca polygonal masonry or even complex topological forms. Digital fabrication allows for a level of precision the Inca Kamayak could only dream of, with computer-controlled milling creating blocks that interlock with microscopic accuracy. The goal is to create a modern vernacular for earthquake-prone regions, one that harnesses the passive, durable intelligence of the past through the tools of the future. These are not replicas of Sacsayhuaman, but rather its conceptual heirs, buildings where every joint is a calculated interface for managing force, where resilience is built into the very shape of each piece. This research represents a full circle moment, not of nostalgia but of recognition. It acknowledges that those ancient builders, through patient observation and embodied knowledge, arrived at a profound truth about stability in a chaotic world. They understood that true strength often lies in flexible connection, not in rigid uniformity, and that sometimes the most advanced path forward is to listen to the quiet lessons already written in stone. The perfection of those joints has, perhaps inevitably, given rise to one of archaeology's most persistent and romantic myths. It is the story of a lost secret, a magical plant whose sap could soften granite like clay, allowing the Inca to mold stones together before they hardened again into solid rock. This idea of a liquid stone solvent is a compelling shortcut, a narrative that replaces immense human effort with a single, mystical ingredient. But as satisfying as that story may be, the evidence written in the stone itself tells a different, and ultimately more impressive, truth. No archaeological excavation at any Inca site has ever uncovered a vessel, a residue, or a botanical reference pointing to such a substance. More decisively, geologists who have studied these walls note that the mineral structure of the andesite and granite shows no signs of the chemical alteration or thermal metamorphosis that would occur if the stone had been temporarily softened and rehardened. The crystalline structure is intact, showing only the mechanical marks of percussion and abrasion. The myth, while imaginative, misunderstands the nature of the accomplishment. It assumes such precision must be impossible through manual skill alone, requiring a supernatural explanation. In doing so, it inadvertently diminishes the real genius on display. The true story is not one of a magical plant, but of a cultivated human intelligence, of generations of artisans who learned to speak the language of the mountain with their hands. They did not soften the stone, they listened to it, learning its grain and its fracture points through patient, iterative effort. The solvent was not a juice from a leaf, it was time, observation, and an accumulated mastery passed down through 1,000 careful strikes. Dismantling this myth is not about taking away wonder, it is about redirecting our awe to its proper place, from a fictional potion to the profound, tangible skill of the people who shaped an empire from the living rock. Their method was harder, slower, and far more human, and that is precisely what makes it so extraordinary. These principles, when woven together, form a coherent and brilliant engineering philosophy. Polygonal interlock, trapezoidal openings, and flexible foundations were not separate tricks. They were integrated components of a single, unified response to a volatile world. Each element served a distinct but connected purpose. The polygonal masonry scattered destructive energy, the trapezoids locked openings against failure, and the engineered foundations absorbed the initial shock. Together, they created a system that was far greater than the sum of its parts, a holistic approach to building that considered the structure, the ground, and the forces between them as one continuous conversation. This reveals a culture with a profound, almost intimate understanding of their environment and their materials. They did not see the mountain as an obstacle to be conquered, but as a partner and a teacher. They listened to the stone, learned its language of fracture and strength, and designed with its natural behavior in mind. Their work stands as a lasting testament to a form of ingenuity that is both ancient and urgently modern, an ingenuity rooted not in domination but in dialogue. It is a reminder that the most resilient solutions often come from observing the world as it truly is, and finding a way to move gracefully within its inherent rhythms. Their silent walls continue to speak, offering a timeless lesson in how to build not just for today, but for all the unpredictable tremors yet to come.